All right, class. So looking at action potential of a myocardial cell. Action potential in myocardial cell. Okay. First thing we need to remember, in case of myocardial cell, there is no threshold. No threshold. These myocardial cells receive the action potential that are originally generated in the pacemaker cells, right? So the pacemaker cells generate action potential that travel to these myocardial cells via gap junctions. And then as the action potential enters these myocardial cell, boom, you have voltage gated sodium channels open up so these myocardial cells maintain a resting membrane potential at negative 85. As soon as the action potential comes in, we have voltage gated sodium channels open. As that happens, what enters the cell? Sodium, right? Sodium enters the cell, brings in positive charge. We have depolarization of the membrane, and the membrane depolarizes to about plus 20 or positive 20. At this point, at positive 20, the voltage-gated sodium channels close, and we have some voltage-gated potassium channels, and these are fast channels. They open. And as the voltage-gated potassium channel opens, obviously potassium goes out. So at this point, here we had sodium in, right? At this point, we are having potassium out. As potassium moves out, obviously we are losing positivity, so the membrane potential drops to about negative 15. And at this point, remember, the potassium channels are not closing. The potassium channels are not closing. They remain open. And on top of that, we have voltage-gated calcium channels open. And as voltage-gated calcium channels open, what comes in? Calcium comes into the cell. So think about it. At this point, we have potassium going out and then calcium coming in. So that kind of balances out. It balances out the charge, right? So that helps the myocardial cells to form a plateau. Do you see the plateau in blue? That is caused due to outward flow of potassium and inward flow of calcium. And that continues for about 200 to 300 milliseconds. After that, the voltage-gated calcium channels close. So at this point, voltage-gated calcium channels close and voltage-gated potassium channels open. Remember, these potassium channels, they are slow channels. They are slow channels. They are not fast. And as these channels open, hold on, there you go. As these channels open, obviously we have potassium going out, and that brings the membrane potential back to negative 85. So let's quickly review. Action potential in myocardial cells. Remember, these cells do not have threshold. They receive the action potential that are originally generated by the pacemaker cells. And as soon as the action potential reaches these myocardial cells, the myocardial cells maintain a resting membrane potential at about negative 85 millivolts. As soon as the action potential reaches these cells, voltage-gated sodium channel opens up, sodium enters the cell, causing depolarization to positive 20. So this is depolarization, right? At positive 20, the voltage-gated sodium channels close, and then there are some fast voltage-gated potassium channels that open out, resulting in outflow or outward flow of potassium. that brings the membrane potential down to about negative 15 millivolts. At that point, we have voltage-gated calcium channels open up and calcium rushes in. So at this point, we have potassium leaking out or potassium moving out and calcium coming in, which kind of balances the net movement of positive charge, and that helps to reach a plateau. And this plateau runs for about 20 to 30 milliseconds, after which the voltage-gated calcium channels close and there are some slow voltage-gated potassium channels that open up, causing movement of potassium out of the cell. As potassium moves out, we lose positivity and the membrane potential comes down to resting membrane potential of negative 85 millivolts. As you see, the action potential is long, right? So during this action potential, as the action potential is proceeding, obviously you cannot stimulate the myocardial cell again. And that is why myocardial cells have a long absolute refractory period. So in this case, the refractory period is very, very long. So this diagram is showing us the correlation between myocardial action potential and myocardial contraction. Now the action potential is long, right? And therefore it has a long refractory period before it can contract again. So the contraction of myocardial cells are long, and also the action potentials are long. And since the action potentials are too long, the absolute refractory period is also long. It lasts for about 200 to 300 milliseconds, which is a lot as compared to skeletal muscles, if you remember. Okay. Electrocardiogram. You have learned about electrocardiogram in lab last week. Now, I want you to understand one thing. Electrocardiogram is nothing but graphical representation of the electrical functions of the heart. Now, we know that the pacemaker cells generate the heartbeat, right? And I also want you to know that our body is a very good conductor of electricity. As those action potentials are generated from the pacemaker cells, the electrical impulse can be actually felt throughout our body, and we can measure it by a process called electrocardiogram. In short, we call it ECG. British English calls it EKG. It's the same thing. So if you look at an electrocardiogram, it actually represents one heartbeat. I will quickly draw out what I usually draw for lab. Okay, so this is one heartbeat. And if you think of an electrocardiogram, it has three waves. This is called the P wave right here. Let me see if I can change color. Sometimes it just doesn't let me. Let's see. Okay, let me do it here. P wave. Then you have QRS complex. Then the last one is the T wave. Okay. So right here we have the P wave. This is P wave. The blue one is QRS complex. Oh, blue. sorry class, this is QRS complex, and this is the T wave. Let's talk about this. P wave is atrial depolarization. When the atria depolarizes due to the action potentials generated from the SN node, that is indicated by P wave. The QRS complex indicates ventricular depolarization, and the T wave represents ventricular repolarization. So P wave, atrial depolarization, QRS complex, ventricular depolarization, and the T wave represents ventricular repolarization. All right. Now, there are two other segments that you must know. This segment right here is called the PR segment. PR segment. And the PR segment is the time when the AV node holds a signal for 0.1 to 0.2 seconds. So during PR segment, remember that the AV node holds the signal for 0.1 to 0.2 seconds. And then we have another, actually let me do it a little better. This is QRS. And then there is another segment right here. This is called the ST segment. And the ST segment is the time right before ventricular repolarization. So this is a time when the ventricles have already undergone systole and it's just waiting for repolarization. So ST phase or ST segment represents the time before ventricular repolarization. All right, you must know this for the exam. All right, I'll stop here and then start. Actually, no, I can do this one. All right, so this is actually showing us a relationship between impulse conduction and ECG. At the very bottom of this diagram, I want you to notice that yellow represents depolarization and green represents repolarization right here. So let's take a look. The very top picture right here. This is showing that the atria is just beginning to depolarize. Do you see that? And that is shown by the yellow upward stroke of the P wave. The next one shows that about 3/4 of the atria are depolarized, and you can see a more prominent P wave at this point. The next one shows complete depolarization of the atria. So at this point, both the atria are completely depolarized, and we do see a very, very prominent P wave. The next picture is when the atria has depolarized, and then the AV node is actually holding the impulse for 0.1 to 0.2 seconds before it can let the action potential flow to the ventricle. So this is showing us the time where the atria is depolarized and the AV node is holding the signal. And that is shown by this PR segment right here. Next, here we do see that the atria has repolarized and the wave of depolarization is moving into the ventricle as shown by the yellow lines. And so this is representing the ventricular